Okay, folks, now we're going to do some sample questions involving Z-scores, the kind of stuff you might expect to see on a test. So let's get right down. Remember, we're going to use our Z table, so we'll keep that handy. We'll take a look first of all at the first one. It says James Bay Huskies, they're way up there in Ontario, have an average lifespan of 10 years. Okay, so a James Bay Husky, whoops, jumped a page, has an average lifespan of 10 years. So I'm going to draw a picture right away. So we got an average lifespan of 10 years. Okay, so there's our 10. Standard deviation of 1.5, so we go like 8.5 and 11.5. Okay. This population is normally distributed. Approximately what percentage live to be more than 12 years old? So we should have a Z-score of a little more than 1 there if we're going to get to 12 years because we're just beyond 1 standard deviation. So let's get that Z-score first. So remember that Z is equal to whatever our population value is, x minus mu over sigma, right? Okay, so in this case, Z is going to be equal to the x value we had, which was 12 years old, minus the average, over standard deviation, which is 1.5. So that's 2 divided by 1.5, which I think should be about 1.33 if I'm not mistaken. 2 divided by 1.5 is 1.33-ish. So that's about 1.33. So for a Z-score of 1.33, it says what percentage of Huskies live to be more than that? So we want to know for a Z-score of 1.33, what percentage is above that? So remember the table tells us exactly the opposite. So let's see what we got here. So a Z-score of 1.33, we go to 1.3 and then 0.3 to make 1.33. So we got 90.82% there. Okay. So we have 90.82% are below that. So we take 100 minus that, and that's going to give us 9.18%. So if we want to say approximately, I'd say approximately 9% of Huskies are going to live from the James Bay are going to live to be more than 12 years old. So it looks like B is our correct option. All right, let's take a look at the next one. Red blood cell counts are normally distributed with a mean of 4.8 and a standard deviation of 0.3. Okay, 4.8, if we got 0.3, then we're going up to 5.1 and down to 4.5. Gotcha. Evangeline's doctor tells her that her red blood cell count is higher than 82% of the general population's. What is her red blood cell count? Okay, so 82% of the population, so we're going to have to find a Z-score where 82% are below you. So that's pretty straightforward. You just want 0.82 for our percentage value in the table. So let's see if we can find 0.82. It's going to be somewhere in between these two. So to make sure you're above at least 82%, we better go this one. So for that one, we're at 0.92. So our Z-score here is going to be 0.92. So we have Z equals 0.92. And we want to find out what X is. And remember, X is going to be mu plus Z times sigma. So our average here was 4.8 plus Z, which is 0.92, times our standard deviation of 0.3. So we're going to find out what her red blood cell count is here. These are always numbers they tell you when you get blood work done that never really make any sense to me, but we can do the math and report the scores anyway. So that gives us 5.076, so we can call that about 5.08. So her red blood cell count is about 5.08, whatever that means. Okay, so those are two problems that you would be expected to be able to solve using Z-scores. Okay, so remember, it's important to keep this formula in your brain. It'll be given on your formula sheet, but it's a helpful one to have. And it's also important to be able to use that Z table proficiently. Okay? All right, hope that's helpful.